So this is lecture 3, example 4, and we're going to look at one more small tweak on the example that we've been considering. So let's consider a sequence AN defined by the rule AN equals 1 on 2n plus 1. So we put n equals 1, that gives us a third, n equals 2 gives us a fifth, a seventh, a ninth, and so on. So if you remember the previous example, it's so similar. If the previous one's tends to 0, then this one's really got to tend to 0 as well. Okay. But there's going to be an interesting difference in the proof. So again, we want to be able to show that the following implication holds. For all epsilon greater than 0, there exists some capital N in the natural numbers, such that if little n is bigger than capital N, then the difference between the nth value of the sequence and your conjectured limit of 0 is less than the given epsilon. And we're going to guess capital N of epsilon is equal to 1 on 2 epsilon, essentially, in the spirit of it, in the heart of it. But we want to turn that into a whole number, so we round down to the nearest whole number and then add 1 for convenience. And that implies that n greater than capital N will always be greater than 1 on 2 epsilon. And we want to know what are the implications for an minus 0, which is 1 on 2n plus 1 minus 0, which is just 1 on 2n plus 1. Now here's where this subtle little difference is coming from the previous one. We've got our little aside over here. 1 on 2n plus 1, we want that to be less than 1 on something times n, just because that plus 1 is really inconvenient. That will hold if and only if 2n plus 1 is greater than something times n. Well 2n plus 1 is always greater than just 2n, so let's replace that question mark with a 2, like this. Yeah, we're happy. So this means absolute value of an minus 0 is equal to 1 on 2n plus 1 is less than 1 on 2n. And when we know here, another little second little aside, n greater than 1 on 2 epsilon is true if and only if 2n is greater than 1 on epsilon. It's true if and only if 1 on 2n is less than epsilon. Less than epsilon, and we are done.